The title of his talk is Paleo-Climate and Future-Climate.
Okay, this is a really risky paper for me. So, if you would see me do a talk under normal circumstances, what you would see is I would give you a very, very detailed case study of some bit of science and then do some philosophy at it. What's dangerous about this talk is that I'm just doing philosophy at some science without really knowing very much about the science, which is a very, very, very bad thing to do if you're a philosopher. But I have a justification, which is as follows. One of the things that we know about doing science is that it's a pretty bad idea to go out and do science and just collect data, right? It's kind of a good idea to have some hypothesis or some research questions to guide your data gathering. In some sense, I'm doing that. What this is me starting to think about the relationship between the sort of Paleo-Climatological data, so data from the sort of deep past of the climate, and this project of trying to work out what's going to happen in the sort of near future. And so there's a real danger, in fact, inevitability of me, do you know this term, teaching grandma to suck eggs? Grandma knows how to suck eggs. There's no point in you sitting there telling them. So some of this is going to be me presenting some extremely coarse, blunt, philosophical tools for what I presume are going to be some sophisticated scientific epistemic practices. And so what I'm expecting to have happen is you guys tell me what to read in terms of the science. And then the sort of things I've said will inevitably develop as we go along. So, if you were using paleoclimatological data, it seems like there's sort of a distinction that's being made between sort of the near past. So this is usually data you're getting from records, right? Things from satellites, so on and so forth. And then we're looking at stuff from the deeper past. So the two questions I'm asking are something like this. We're in the business of sanctioning or calibrating our climate predictions. What do we get out of looking at the deep past? What can the deep past do for us that, say, looking at the recent past cannot? And then, well, what challenges are there? And we're interested in two types of challenges. What challenges there in discovering facts about the past in the first place? But then I think more interestingly, what challenges are there to establishing evidential relevance between the deep past and the more recent future? Okay, so most of you probably already know this, but here's just some of the ways we can access the deep past of the climate. One thing which is important about geological science, here's an erratic rock, for instance. Gosh, how did that big rock get there? It's different from all the other rocks around it. Well, a glacier dropped it off. This tells me that there used to be a glacier there. Turns out that the speed of stalactite and stalagmite growth tracks the amount of rainfall density, obviously because they're formed by water moving through caves. And so, looking at stalactites, I can work out how much is raining in that area. And fossilized pollen tracks things like biodiversity. So, if I have a whole lot of pollen that's very biodiverse, this suggests that in the past it was very warm and moist or some other thing about a climate. So that is focused local data, right? That's telling me about a particular place in the past. But we can also look at a much, much more general scale, right? And this generally involves digging a big thing. One of the big things you might dig is a core sample from below the sea, from the seabed. This is going to give us information about microbial diversity, dust and mineral deposits. And ice core samples, which is the more sort of typical one. There's things like the sort of ratios of oxygen isotopes get captured during snowfall, and so we can recover these and thus find out a lot about the past. Okay, so that's coarse general data. Kind of, I take it, obvious things to point out about this climate information or this climate data. It's patchy, that is to say, it's not like we have the same resolution at all scales, and it's not as if we have the same resolution temporally, and also there are going to be lots of biases in there. It's large, there's a lot of data, it's also diverse, and it's in some sense reconstructed. Don't freak out, I don't need anything too scary by that. I just need our routes of getting to, say, how this, facts about the way the stalactite look, to how much rain there was 10,000 years ago. is extremely indirect. There's a lot of weightlifting to be done by your background theory. And that's going to matter. So, what kind of role, this is the first question, can paleoclimatology play? And in particular, what can it do for us, which the last couple hundred years can't do? Wow, that was cool. Macs are very good at translating PC animations. That one worked. So, what we're interested in is this rich, but very, very messy and very heterogeneous sort of access to the past, but it's on this very, very long scale sometimes, and how they could possibly be linked to this much, much smaller scale in terms of temporal scale, or maybe not global scale question. Here's the first thing I think that it can do. And again, I think this is kind of obvious. The second one's more interesting. I've got a climate model. It's got a target, something about the future climate, right? What temperature will it be in 2050 or whatever? It seems as if one thing I can get from paleoclimatology is what I'm going to call an analog. What's an analog? Well, an analog is just some event or episode in the past which is relevantly similar to our target. So, an easy example might be something like some time in the past where the atmospheric composition is similar to the way we expect it will be in 2050, or something like that. So these particular events, which are similar to our target, give us reason to think that it seems our model is able to track that target. And one reason why paleoclimatology is going to be important for this is, of course, well, it's got a longer scale, so it's going to have more possible analogues in it than the last few hundred years. And so one thing that paleoclimate does is it gives us analogues. It says, hey, here's a similar scenario, a similar event. That gives me reason to think that my model is going to behave in the same way. So you might think. This other one I think is a bit more interesting. Another thing that you can get when you're looking at a very, very long scale process is you can test your model over a range of different climate scenarios. And it seems as if success over a range of different climate scenarios gives you reason to think that your model, or some component of your model at least, is kind of getting things right. It's latching on to the way the system works in the right kind of way. And if you've got a model in there and you think that you've got good reason to think this is latching onto the world in the right kind of way, it seems like that justifies you, or at least licenses you, in extrapolating to some unknown thing. Right? So this is what I'm going to call a sort of realism hypothesis. You've got reason to think that your model is connected up to the world in the right way, or at least some aspect of it is. And it seems getting a success across a diverse range of scenarios gives you reason to think that, even if these scenarios are somewhat different from our target. So those are two kind of roles that I'm thinking of. The first is you provide analogs. You've got relevantly similar scenarios to your target. The second is by getting these sort of long-term patterns right, by getting it right over a diverse bunch of different scenarios, that supports a realism hypothesis. You can say, my simulation captures like the essential dynamics of climate systems, or something like that. So those are the two things that I can see paleoclimatological information doing, which seems to be a bit different to what we get from the last few hundred years. Now some challenges. The first challenge involves a little bit of really simplistic philosophical machinery, which goes as follows. Traditionally, we think about this relationship between theory and data in a very, very simplistic way. So for instance, maybe I've got a theory of celestial mechanics, and my data is those little twinkly things I see in the sky and where they are. We typically think that my theory of celestial mechanics explains where the little twinkly things are, and then where the little twinkly things are then supports my theory. Bogen, Woodward, and many, many other people have pointed out that this is, of course, far, far too simple. My theory of celestial mechanics doesn't explain my data because it doesn't explain, for instance, how I've gone about collecting the data. It doesn't explain anything about telescopes. It doesn't explain anything about optics. Right? And so what they do to sort of solve this problem is they introduce the idea of a phenomena, and the phenomena is kind of the cleaned up data. Right? It's the data that's been has the noise removed, it's been made sort of relevant to the theory. And so we have this slightly more complicated picture where the theory is explaining the phenomena, the data forms the basis of the phenomena, and the phenomena then supports the theory. Why am I telling you this? Well, one thing that I noticed when I was going through reading the philosophy of climate science, so again, I haven't read any of the science of climate science yet, but I've read a lot of the philosophy of climate science, is there's an enormous amount of focus on the relationship between the phenomena and the theory. One way of putting it is the question is, let's assume we've got good information. Let's assume that our phenomena is good. But let's see what we can find out. The first thing I want to just briefly touch upon is the relationship between data and phenomena. And again, lots of people, a few people at least, particularly, I think scientists are much more worried about this than philosophers are. And they will point out these worries in terms of recent climate. And so I want to briefly talk about it in terms of deeper into the past. As I already mentioned, the relationship between the data and the phenomena here is incredibly indirect. Right? There's a lot of steps to get from an ice core, say, to a range of temperatures in the past. And this suggests that the relationship between the data and the phenomena can be somewhat unstable. That is to say, if our background theories change, it seems like we're going to end up with very different looking phenomena. Also, as I previously mentioned, the data sets are really big. Right? And again, this should be a very familiar point. If you've got a really, really big data set, then just in virtue of the size of the data, there are going to be many, many possible patterns in there. And so splitting signal from noise is going to be extremely difficult. Right? What does it suggest? Well, I think this is the third or fourth time someone's used the word underdetermination in this conference. But this leads to a kind of particular type of underdetermination, where it's underdetermination of the phenomena. Right? This isn't sort of an underdetermination of our theories or anything like that. This is just underdetermination of working out what is actually meaningful, what's the important bits in my data. And so this is the first, I think, one way of capturing the first sort of challenge you might give. If I was to say, hey, let's put a lot of emphasis, say, on paleo-climatological data, you would say, well, hang on, it doesn't look like there are sufficient grounds for me to prefer one characterization of the phenomena, one way of maybe drawing a relevant pattern out of the many possible patterns in the data over another. So now I'm going to talk about evidential relevance. So this is, given that I've got this information, given that, say, I've got some pretty good picture of the past, why should I think it's got anything to do with what's going to happen to the climate for the next 50 years? And I've got two challenges here, two worries. The first, which I don't have very much to say about, is scaling. It's kind of obvious. It seems as if the picture, or the things we're going to be able to get epistemic access to in the past, could quite easily be at a very, very different scale than the things that I'm trying to then predict. And that can be a real problem if I'm trying to use the past to get access to analogs. Remember, the point of an analog is that it's relevantly similar. Right? It's going to be, so for instance, the analog might be sometime in the past where the amount of carbon in the atmosphere was relevantly similar to where we think it will be in 50 years. That might be all well and good, but if my access to this past is extremely coarse-grained, and I can only look at it over, a few hundred years, that's not going to help me if I'm interested in finding out what's going to happen in 25 years, at least on the face of it. And so there's this problem of the scale of the analog mismatching with the scale of the future target. And so we have these potential differences in resolution and scale. The second worry applies to both analogs and the sort of hypotheses of realism or whatever. You notice that for me to say this gets it right in all of these scenarios, that gives me reason to think we'll get it right in this scenario, I'm committing to something about the nature of climate systems. Right? I'm committing to something like this. I'm committing to some kind of uniformitarian hypothesis. Right? I'm saying, look, this system is regular enough such that I can extrapolate to a new case. Right? So you might say something like, some particular system, this is just one of many ways of trying to capture a uniformitarian hypothesis. Processes which affect S at one time are going to do roughly the same thing at another time. Now, it seems as if these sorts of hypotheses can fail in a whole bunch of ways. Here's one way they can fail. The system could just be crazy, right? The system could just not have stable dynamics. The system could be all messy, right? In some sense, you're probably making a mistake of thinking it's a system, if that's the case. I would be really surprised if that's what we're seeing in the climate case, right? At least over relatively short timescales, perhaps, it seems as if the climate is regulatively subexceed. But I think there's a much more interesting way in which these hypotheses could fail. And that would be if the climate's dynamics were path-dependent. So, if you're path-dependent, maybe the best way to do this is with an example. Let's talk about giraffes. Here are some giraffes. As I'm sure you know, the way that sort of giraffes have these breeding dynamics, this is, being a bit coarse with the actual data, but whatever. Roughly, the male giraffe, who's best at whipping the other male giraffe with his neck, something like that, is going to maximize his breeding potential, or something. So there's some stable dynamics, right? Over time, giraffes with the big strong neck's probably going to win. Question, does it seem like I should predict those same breeding dynamics in an animal which is closely related to the giraffe? Well, no, of course not. Because this sort of particular set of dynamics relied on a very particular setup in order to get there. Right? There's a very particular order of events you need in order to get this particular giraffe breeding dynamics. Would I be safe in inferring this deep into the future of the giraffes? Maybe in 100,000 years will giraffes be doing this? That doesn't seem very safe either, right? Because these dynamics seem kind of fragile. And so, although they've got relatively stable breeding dynamics over relatively short timescales, both the emergence of the dynamics requires a very specific cascade of events, and moreover might be fragile further along. And the conditions under which they operate undermine us extrapolating, in this case, about the relatives of giraffes and forward into giraffe history. And so the thought is, maybe the climate dynamics are like that. Maybe it's the case that it has relatively stable dynamics over short periods of time, or maybe in particular locations, but I can't take that as, I'm not able to use that information to guide us to the future. So if that's right, it seems like maybe I can use the last couple hundred years, perhaps, if I'm lucky. But I certainly can't use 15,000, 20,000, whatever. Right? So there is kind of a little framework, right? There are three sort of challenges that it seems you're going to face if you're going to try and use paleo-climatological data in order to support or to sanction models telling us about the future. Clearly, I don't think this is, basically I'm going to find out whether this is a problem once I go and actually go into the science a lot more detail. But one thing to immediately point out is that the extent of these problems is empirically tractable. The most obvious case is, think about uniformitarian failure. If it turns out that climate systems are path-dependent, it seems like I should be able to tell that by looking at the climatological record. Right? There are going to be certain predictions. There are going to be ways that these sort of path-dependent systems are going to look. So that's good. Also, it would be a mistake to think that analogues need to be precise, that analogues need to be at exactly the right grain of resolution. I think when you look at the way that other historical scientists, say paleontologists and archaeologists, use analogues, they tend to use them in a very patchworky kind of way. And so it's not that much of a big deal, I think, if my analogues were missing. And finally, evidence is cumulative, right? Just because this evidence might be a bit crap, let's imagine, that doesn't mean that it can't be usefully incorporated in terms of defending various hypotheses. So, I suppose I've argued something like this. Paleo-climatology has a lot of potential. It can bring things to the table which the more recent past can't, right? It's got much more potential to provide us with analogues, and moreover, it's got much more potential to support these kind of realism hypotheses. But there are some challenges, right? First, there's the nature of the data itself, or the phenomena itself, right? Because we've got large data sets, that suggests we're going to have a lot of possible patterns, and because there's so much indirectness, that looks like that's also going to breed underdetermination. And so there's a worry about how we get sort of meaning out of the data. And there are two challenges to the relevance of the climatological phenomena. Right? First off, is our access at the right grand resolution in order to provide those analogues? Second, are our uniformitarian hypotheses licensed based on the sort of path dependence challenge? And so the final question, this is sort of basically where I go to from here, assuming that everything I've said isn't completely silly, is to ask, well, how do, or maybe can, if they're not already, climate scientists go about determining the extent of these worries? And finally, obviously, how are or might they be mitigated? That's the talk.
So, I mean, we've been working on this quite a lot recently, particularly with the combination of the paleo runs and CMIT 5. I mean, a lot of what you're saying, fits in with how we've been approaching it. But it's much more on the well, okay. So we suppose mostly don't think about it in terms of analogs. But it turns out that there's no good analog in the past for anything that we really care about, and so you might as well not bother with that one too much. But the realism hypotheses, so that's like just a tick. You can do that. Tick. You can do that. Tick. You can do that. That's okay. But actually, I think we want more. We want something that's quantitative that says, can we demonstrate that something that we're predicting in the future is a robust prediction for which we have confirming evidence, right? So I showed an example of that before. Another one would be, can we show that models that are differentially sensitive to the future are also differentially sensitive to the past, and that you can select amongst models based on paleo data, right? And then all of this time you're always worrying about, are you actually doing a commensurate model observation match, right? So what is it you're actually measuring, and what is it you're actually producing from the model? And often you have to do a lot of work in order to make sure that that is the case, right? Because a lot of times people who are working in paleoclimate say, oh, this is related to temperature, when it's really a very complex relationship to temperature, and there are multiple variables that also add up to it. So you have to have that forward modeling piece. You have to have, and you're looking for both that confirmatory and that discriminatory aspect of the models.
Great. So that's really helpful. So I was definitely assuming that people were working on this. So obviously. So it's interesting that you say that there are no. So if I'm going and looking for sort of relevantly similar climate scenarios, that's just kind of. Is it because why aren't there analogs? Like we just can't find them, or there's aren't any, or humans are crazy?
No, so you're looking at a situation where you have substantial amounts of ice on the planet, which pretty much puts you only in the last 3 to maybe 10 million years. Over that period, carbon dioxide has, perhaps in the Pliocene, is as large as that. That's about 3 million years ago. But over the period, kind of in the interglacials, where you've got Greenland, where you've got West Antarctica, it's never been that high. And of course, the different forcings that we have now, which are both land use forcings, aerosol forcings, greenhouse gas forcings, none of those things have ever occurred in combination.
Right. So there's this kind of this sort of scientific horror case of facing something which is a sort of unique situation, right?
I don't know if it's a horror.
Well, to be traditionally, it's
without very strong evidence to the contrary, we appear to be an unprecedented event.
Right. That's helpful.
Oh, that was your answer. I think I saw Jesse. Did you have a question?
Just a quick comment. You'd mentioned the data phenomena distinction between Bogen and Woodward as a starting point for yourself, and then you went and talked about the underdetermination of the phenomena from basically because there's a lot of possible patterns, especially with large data sets. strikes me as very analogous to the argument that McAllister went on to make against Bogen and Woodward's data phenomena distinction, where there's a lot of patterns. How do scientists choose? They must pick the one they think is the best, based on the one that they think is prettiest or whatever. These are crazy reasons. Scientists don't know what they're doing. Phenomenal underdetermination. Everything is bad. And then there's this big argument with Woodward and so on and so forth. There's an excellent paper by Todd Harris, 2003 PSA, where he, you can talk to me later and I'll give you the citation, where he brings in Patrick Suppi's data models framework and basically puts all that water under the bridge. He says, look, the data phenomena distinction is useful because it helps us, it enriches the picture that philosophers of science are working with. And McAllister's got a point, but he's taking it too far and he's making too much of it. If we also incorporate thinking about the goals of the scientists and the purpose of this work, that can help clear up a lot of the possible problems with that underdetermination. And so that's something that's worthwhile to look into.
Yeah, that's really helpful. I mean, obviously there's a sort of, one might want to avoid getting too far into sort of the soupy stuff because it gets very, very hard very quickly.
That's why I recommend the Harris.
Yeah. So when I'm talking about this sort of phenomenon of determination, and also the Bogen and Woodward's distinction, I'm really using them as sort of tools in a way, right? So I'm interested in the reason I like the data phenomena distinction is simply that it brings this thing deeply into, it really brings into focus what has to happen to data in order to get it relevant to our simulations or our theories or whatever. In terms of, one way of putting, the underdetermination thing is just saying it's hard, right? Because I'm talking about sort of local, what's sometimes termed local transient underdetermination, where it's just, given the data we have, things are underdetermined. Now that doesn't mean that you couldn't develop other technologies, find more evidence, so on and so forth, where that could be resolved. But that paper sounds really helpful, so thanks.
James Farmer?
Thanks for your talk. This is a historical note about understanding Earth system processes. Our understanding is based on geology and geological type things, which is only in the order of 200 years since this definition of deep time. So the one graphic that you showed, which was the boulder, would have had a completely different interpretation 200 years ago. It would have been some aspect of drift, where a large ice sheet or a floating ice island might have deposited over a world ocean. So if you were a paleoclimatologist in 1820, you might say, you might say, well, that was evidence of a world ocean rather than an ice sheet. And so the paleo record is only going to speak to us through the interpretations of the earth scientists who are interpreting that record. And I just hope you take into account that today's science might be tomorrow's history of science, and as I like to say, and that you're looking at a shifting target, assuming that today's interpretation is the best you can work with, but also realizing that things have changed dramatically. So glacial till used to be called glacial drift for that very reason.
Good. So you'll recall that I gave sort of two reasons why we should sort of expect there to be a lot of phenomena under determination. One was there's lots of data and so there's lots of patterns, but the other one was this idea that our background theories could be rather unstable, which is to say that could be rubbish. This is what archaeologists call mid-range theory, for instance. It's your bit of evidence, bit of theory that you use to connect what you trace to the past, right? And yep, that could end up being false. I'm sure some of the things we think now are currently false, but I think some of it's probably right. I'd be astonished if we were wrong about the stalactites. Right? I think that there's reason to think that for at least a lot of our geological mid-range theory, at least with some of these easier cases, it looks like that's pretty stable, and I'm probably willing to make an empirical bet that that'll end up being right.
Roman, did you have something? Captain Schmidt, did you have something again?
I was just going to address James' point. So one of the ways that you deal with that interpretational instability, if you like, is by incorporating more and more of the process that produced that, that whatever geological observation that you have within the theory itself, right? So that you try and model the data and incorporate that. The more you understand the data, the more you incorporate that into your theory, and so then that becomes a self-consistent view both of the event that caused the observation and also the process by which the observation is recorded. So, and that does change the interpretation, right? So one of the examples that we've worked on was the 8.2 kiloyear event, right? Which there was a huge lake that was blocked by ice above by Hudson Bay, right? So this is in the deglaciation, not so much of water. It collapsed very suddenly, changes the climate of the North Atlantic, and this is seen in the Greenland ice cores. Now, in the Greenland ice cores themselves, the measurement there is in oxygen isotopes in the water, in the ice, right? Now, there's a classic interpretation of that as purely being a temperature signal, but because of all this fresh water, because of the change in the circulation, when we actually calculated using a forward model for the isotopes, it turns out that half of that signal is actually a source where the water came from change, as opposed to a temperature change. And so the interpretation in terms of physical variables changed as that data was incorporated into the modeling framework, and we end up with a more consistent, more coherent view of the whole thing that actually deals with a lot of the supposed inconsistencies between different data sources.
Adrian, quick response.
I think to sort of summarize what you were saying, I take it that worries about sort of our mid-range theories is being thought about far too simply when we talk about it in these ways, because actually there's a sort of dynamic process of actually doing the modeling and those theories themselves getting kind of built in. And that seems right from the sciences I do know about. It's very much what paleontologists do, for instance.
Okay. Please join me in thanking our speakers.